In modern astrobiology, one principle consistently appears across planetary science, chemistry, and biology. Where there's liquid water, there's a potential for life. And this is not just a speculation, it is a working hypothesis supported by decades of research from NASA, ESA missions, and exoplanet surveys. However, water alone does not guarantee life. Instead, it defines the physiochemical framework in which life, as we know it can emerge, persist, and evolve. Today, we examine water from a strictly scientific perspective, as a solvent, as a thermodynamic regulator, and a universal astrobiological marker. Water's astrobiological importance begins at the molecular level. We know H2O is a polar molecule, producing strong hydrogen bonding. This enables high dielectric constant, which means efficient ionic diffusion, and also liquid stability over a board temperature range, high specific heat capacity, which is also a thermal buffering of planetary climates, solid water less dense than liquid water. This prevents ocean freezing from bottom to up. These properties are rare among known planetary solvents. In astrobiology, alternative solvents such as methane or ammonia are considered, but they operate under significantly narrower temperature and energy constraints. This is why NASA's habitability models prioritize liquid water stability under surface or subsurface pressures and temperature conditions. Water is not only unique to Earth, surprisingly, it is a cosmically abundant molecule, meaning it is common through the universe itself, formed through oxygen hydrogen chemistry in interstellar clouds. Within our solar system, Mars retains polar ice caps and subsurface ice deposits, confirmed by orbital radar data such as the Marses and Carad. Europa, which is a moon of Jupiter, likely contains a global subsurface ocean beneath an ice shell tens of kilometers, which is kilometers thick. Enceladus actively ejects water vapor plumes which contain salts and organic compounds detected by Cassini. Comets such as 67P contain hydrated minerals and volatile ice, supporting the hypothesis of volatile delivery to early Earth. These observations support the late heavy bombardment water delivery hypothesis through isotopic ratios, meaning D, H in cometary water versus Earth oceans, suggest a mixed origin. In exoplanet science, habitability is often defined through the circumstellar habitable zone, the region where stellar irradiance permits stable liquid water on planetary surface. However, modern models extend beyond this simplified definition. NASA and exoplanet researchers now evaluate atmospheric pressure, which controls boiling and freezing thresholds, greenhouse compositions, planetary albedo and orbital asymmetry, tidal heating, and icy moons. The famous James Webb Space Telescope can detect spectroscopic signatures of water vapor and exoplanets' atmospheres using transition spectroscopy. However, the presence of water vapor is not equivalent to life. High temperature steam atmospheres or photo-dissociated water environments may still be biologically sterile. Thus, astrobiology increasingly uses the concept of the habitable environmental framework rather than a single habitable zone boundary. The origin of life research strongly implicates the water as a reaction medium and a catalytic environment, but not as necessary as a direct chemical participant. Leading hypotheses include alkaline hydrothermal vents, which talks about how proton gradients across mineral membranes may have driven proto-metabolic cycles. And also we have the RNA world hypothesis, where water enables nucleotide polymerization under specific geochemical conditions. And we have also the wet-dry cycling models. Surface water evaporation cycles concentrate organics, facilitating polymer formation. These models are supported by laboratory stimulation and geochemical analysis of early Earth along its environment. Water's role here is not passive, but it acts as a dynamic chemical system enabling energy gradients and molecular self-organization. Across the galaxy, thousands of exoplanets have been confirmed, many within estimated habitable zones. However, astrobiology faces a fundamental limitation. Water is a necessary condition for known life, but it is not a sufficient condition. Even if liquid water is common, additional constraints remain essential, such as stable energy sources, either from stellar or geothermal, bioessential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Long-term environmental stability in these exoplanets matter also. Non-destructive radiation environments. Future missions, including atmospheric spectroscopy on Earth, like exoplanets, aim to detect biosignature combinations such as equilibrium chemistry, meaning a coexistence of O2 and methane, because these two gases require biological processes to be detected and present on the exoplanets. Surface reflectance anomalies and also seasonal atmospheric variation patterns. Yet caution is essential. All biosignatures currently proposed have abiotic false positive pathways. So, we know now that water is not merely a substance on Earth. It is cosmically common, chemically unique medium that defines the boundaries of known habitability. From Martian ice to subsurface oceans on icy moons, and from exoplanet atmospheres to the chemistry of early Earth, water remains central to one of the science's most profound questions. Not just where life exists, but how life becomes possible at all. And in that question, water remains our most powerful clue.